Hello, my name is Dan Cary. I'm a fourth-year chemical engineering student graduating in the spring of 2021. This video was made as part of the Student Active Learning Initiative put on by the William G. Lowry Chemical and Biomolecular Engineering Department, and I'll be briefly covering unit conversion and significant figures as they pertain to the type of problem you'll see in your upcoming CB 2200 class and beyond. All right. Here's a summary of the points I'll be hitting, starting out with the purpose of this video, looking at a unit conversion case study, and then talking briefly about setting up these unit conversions. Then switching over to the other topic, we'll review our Sig Fig rules, talk about doing Sig Figs in Excel, and then do a longer example problem. Finally, I'll talk about applications of these concepts and skills in the curriculum and provide a little bit of personal insight with that. All right, so you may be asking, why go over these topics again? Like you've already heard a lot about these things even back in high school. So I would say, as an engineer, being able to manage your numbers and do calculations correctly is a big part of your foundation in the profession. And I quote one of my trusted mentors here in saying that details are of paramount importance. It won't matter how good your ideas are or your experiments are if you can't present your results clearly and correctly. So that's why it's important to get a lot of practice early, just even doing basic problems like these for unit conversions and Sig Figs. And for unit conversions specifically, learning the different scales for physical values early on in the course will set you up to do well with more advanced topics later on, just so you can really go through them quickly. As an example, you might expect to see 5 or 6 different units just for SI pressure on a regular basis later in the curriculum, which I've shown here, and I'll reference a few of these different types of units later on in the video. All right, here's a case study of why we double check our unit conversions. So a little bit of the story. There was an incident in 2003 at the Space Mountain ride at Disneyland Tokyo where one of the cars derailed near the end of the ride, which thankfully did not cause any major injuries, but still caused quite a buzz. It was found as part of the investigation following that one of the fittings between the axle and the front wheel bearing was almost a millimeter outside of specifications, which was because the same part was used between the Tokyo ride and the original California ride, which the California ride had been built with all English unit constructed parts, whereas the Tokyo ride was constructed using metric units. Needless to say, someone had gotten lazy and not double-checked the plans, which resulted in an unnecessary hazard. Another famous and more expensive instance of a unit conversion blunder was NASA's Mars Climate Orbiter, which launched in 1995 and which failed in its mission to orbit around Mars due to navigational error. The error was a result of a faulty conversion from English to metric units, which put the probe off course by some 60 miles, causing it to crash into Mars' surface. Overall, moral of the story is that companies and society in general just expect scientists and engineers to not make that kind of mistake, which is largely why you'll be practicing unit conversion so much. All right, setting up unit conversion problems. I'll preface this by saying that there's no one right way to do this, but this was just the way that I learned. I found that keeping units in brackets helps keep track of the moving parts of the conversions and the equations you're setting up, especially once you get into more unfamiliar units, especially Imperial units. Separating the brackets helps illustrate that you're really doing 2 parallel functions, one that's the numerical computation, and the other that just involves getting the units to cancel properly. The example here is of converting a volume flow rate to a molar flow rate for nitrogen at STP. We're told the units in which we want our final answer to be. The first step here is to recognize that you can use the conversion factor of 22.4 liters per mole for a gas at STP, which hopefully you've seen in Gen Chem. So In order to get volume flow rate in terms of liters, we apply this 1,000 liters per cubic meter conversion factor, and then also apply our conversion factor for hours to minutes. And that gets us into the right units for time. You'll notice that I actually use the reciprocal of 22.4. Setting this up as a multiplication left to right is typically a good way to check that all the units that we don't want in there do end up canceling. So we see that cubic meters cancels here, and cancel liters, cancel hours, so we're just left with the units that we want. Now that we have our final answer of 74.4 moles per minute, we can ask, does this final value make sense? You'll always want to kind of ask yourself if your answers do make physical sense. For instance, if I had made a mistake and forgotten to convert liters to cubic meters, had forgotten this second term, I would have gotten 0.0744 moles per minute rather than 74.4, and hopefully I'd be able to recognize that that value is much too small for the volume flow rate that we had. And being able to predict about what order of magnitude your answer should be in it's an important skill that's developed mostly through practice. Now, on a different note, I'm going to review these rules for Sig Figs, which for individual numbers can just be boiled down to these 4 points. So we know that all non-zero numbers are Sig Figs, and that any zeros between these non-zero numbers are Sig Figs. If zeros are explicitly written following the non-zero value, specifically to the right of a decimal point, those zeros are also considered significant. You can see that down here in example number 4. Same thing goes with zeros to the left of a written decimal point, like in number 3. So we don't have a decimal point in number 2 here, so it's just read to be one significant figure, whereas in number 3, all of these zeros are significant. Sometimes there will be an overline to one of the zeros, which shows that that zero is the last significant figure. So the way that I've written 10,000 here would have 3 significant figures. That zero would be the last significant one. Okay. With that out of the way, I'd like to cover a common mistake that students tend to make when presenting data with Excel. I've made this mistake myself multiple times and haven't always caught it, and I've had points taken off on Uniops lab reports as a result. So take a moment to look at these 2 tables, figure out why you wouldn't want to put these tables into a report. I put the formulas for the cells below the respective columns here. You'll notice that in both these cases there are just way too many Sig Figs in the columns with their calculated values. Excel will just automatically show those decimal places, so you have to kind of follow behind it and make sure that only the correct decimal places are shown. We'll talk about which decimal places to show here. Yeah, too many numbers. So these are the rules that define how many of those Sig Figs you can show based on the type of operation you're doing. For addition and subtraction, the limiting factor to that is the lowest common significant digit place between all the numbers being added. For instance, for the addition problems shown here on the left, the last significant digit place shared by the 3 values being added is the 100th place. So after you've added all these numbers together, you're going to round off to the 100th place. This principle can be summarized by saying that the precision of the sum should reflect the least precise term being added. This can lead to some seemingly unintuitive results, like when you're adding, or rather subtracting 12 from 1,000. If 1,000 has only 1 or 2 Sig Figs, then your answer is just going to be 1,000. And yes, it's weird, just roll with it. For multiplication and division, on the other hand, the term with the lowest total number of Sig Figs, that's the limiting factor for how many Sig Figs you can show in your answer. So in this equation, the second term, 6.0, only has 2 Sig Figs, whereas 1.19 has 3, and this term has 4. So we round our final answer to 2 sig figs. We just get 16. Now it's worth noting that there are exceptions to these rules. There are a lot of times when you don't regard like a conversion factor or a literature value as the term that limits your sig figs. For example, if you're told in the problem to approximate the gravitational constant as 9.8 meters per second, say it's like a free fall problem, that constant alone is not a reason to round to 2 sig figs. For instance, if you have some time value that has 3 sig figs, then you'd want to go 3 sig figs because you're basing your total number of sig figs off of your variables, reflecting the precision of your variables rather than the precision of your constants for that situation. So with those rules in mind, here are a few options for correcting for sig figs in Excel. I recommend using some form of the round function, which accepts 2 arguments, one for the number being rounded and one for the digit place that you want to round to. I have a few instances of that function shown here. Really the best way to go about using the round function is to set up a separate column with the number of sig figs you want for the entry in that row, and use this Excel command that I have in bold here to automatically round to the right place for sig figs. Other options include the round down, round up functions, which just turn all the digit places below a certain place to 0, and the uses for that are really much more niche, so you're really best off with the round function. So I went in and fixed one of the faulty tables that I showed a few slides back. The basis for what I've done here is that I have 2 sig figs for my radius values in the second column, and I've set up a separate column over here reflecting that. So with the rounding function, I'm able to give the right number of sig figs for my final volume flow rate. I also went through the 2 columns for radius and fluid velocity and selected the option to show more decimal places, so it was a bit more obvious that I do indeed have 2 sig figs there. Another note here is that if we're really only interested in that final volume flow rate, we don't need to round the values for area, since that's just an intermediate value. However, if you are going to present a table like this in a report, you'll still want to make sure that you're not going to show way too many decimal places for those intermediate values. All right, so I'm going to go through another example problem, just more the kind of problem that you'll run into in 2200. I'll discuss how we apply unit and sig fig rules to it. So we're tasked here with finding the molar flow rate of air through a blower, which is moving 1,800 cubic feet per minute at the given temperature and pressure. Then in the second part, we're taking this formula for cost and plugging in the volume flow rate of the blower to get a cost estimate, the volume flow rate being this V dot here. And right away in the second part, we can recognize that within these parentheses, we have units of cubic meters per hour in the denominator and an exponent of 0.6. And now, because we want our final answer for cost to be in dollars, C to be in dollars, the leading term here to the parentheses is already in dollars, so our units for V dot on top should match the units for the denominator. So we'll need to convert volume flow rate from cubic feet per minute into cubic meters per hour. But even before we do that, we'll want to convert temperature from the 160 Fahrenheit value we were given to Kelvin, which we'll need to in order to apply the ideal gas law. There is an absolute temperature scale in Imperial units called Rankine, but I've never found much occasion to use it, so for this case we'll just find our temperature in Kelvin, which in this case will be 344.3. So now we do our volume flow rate conversion, shown at the top here, and we come out with a value of 3,058 cubic meters per hour. Now you may be saying, wait, doesn't that 1,800 cubic feet per minute that we start out with only have 2 sig figs? And of course, this is the thin line to walk the sig figs, where the problem isn't always clear if this 1,800 over here was meant to have 2 sig figs or 4, or what. I would say that when in doubt, keep more Sig Figs for any values you calculate before your final answer, in those intermediate values. Record those as part of your work, and then round that to the lower number of Sig Figs for the final answer itself, which is what I've done here for the ideal gas law. So I worked in a conversion for bar to Pascal for my pressure there as well. So we get a final value for molar flow rate of 1.3 times 10 to the fifth. All right, looking at part B, we now have our converted volumetric flow rate, which we can plug into this formula for cost to get $4,889, which we would then round to $4,900. This is an instance of where the number of Sig Figs you showed for an answer can rely on context. This kind of an empirical model is not meant to be very precise, but rather just gives an estimate. So even if we knew we had 4 Sig Figs that we could show, I think it would still be valid to estimate the price at $4,900. Likewise, the opposite can happen where you bend the rules and use more Sig Figs. Like there will be instances in lab where you get a value that's only 1 Sig Fig from your measurements, and a TA may tell you you can treat it as using 2 Sig Figs instead, in which case that's valid, it helps the math work. It's often just a judgment call on your part as to when to make an exception. Anyhow, I'd like to emphasize that unit conversions and these Sig Fig rules are important in pretty much every class you'll take in the department. And doing these kind of problems helps build some really important skills for your later career. Knowing what a unit represents on a physical basis is a mark of competence in industry. And having the ability to quickly conceptualize numbers that are kind of thrown at you throughout your day. As an engineer, it boosts your ability to plan, think on your feet, manage projects. I kind of joke here, knowing your PSIs from your Pascals. You don't want to be stuck in a situation where you don't know that a PSI is a much greater amount of pressure than a Pascal or something along those lines. And really the ability to conceptualize, it's also key to catching problems with a design, or if you have an answer on an exam that seems funky, even if it is just on a rough order of magnitude basis. On a more personal note, and tie this in with my student experience, I just completed my capstone project for the major as part of a 4-person group, and we focused on designing a nicotine extraction process from start to finish. And unsurprisingly, that involved doing a lot of unit conversion for mass flow rates and estimations for equipment sizing, kind of similar to the practice problem for the blower I showed earlier, but a bit more complex. The skills in Excel were also immensely important for organizing all the information for the process. When we were pulling it out of simulations or online sources or whatnot. The gist is that the things I've shown here will keep coming up in the curriculum and in research if you're looking into doing that. Having never actually interned in a chemical engineering sort of job, I unfortunately can't personally comment on applying these skills in industry. However, I'd like to take this opportunity to say that you don't need to get some great internship or co-op to get a job or succeed in this major. Of course, it helps if you know you're really passionate about a specific area, but it's not imperative. Like I'm going to work as an engineer for Epic Systems in Wisconsin once I graduate. So don't worry if you don't know what you want to do with this major yet, because I certainly didn't 2 or 3 years ago. More than anything, Chemie is about acquiring problem-solving skills and a solid work ethic, and companies and grad schools will recognize that. Of course, the work gets tough, but I encourage you to stick with it. Don't be afraid to ask TAs for help. Go to office hours and take time to pursue your passions outside of academia, because that's really what keeps your motivation up to succeed academically. And that's all I have. Thanks so much for watching, and I wish you all the best in 2200.